All right, so let's draw a picture to begin with. There's a television camera, fancy little camera right here. Oh, that looks like a fancy camera. 4,000 feet from the base of a rocket launching pad, and then we're gonna have to draw a fancy rocket. Awesome. Gonna have like double, triple. Oh, looks like Christmas tree rocket. There we go. Very famous ones. Flying up into the air. It's a very big rocket if this is 4,000 feet. This is all good. All right, so there is a very big rocket, and it has risen 3,000 feet, and its speed is 600 feet per second. So again, it makes a triangle. It's like a triangle question here. We've got our x squared plus y squared equals z squared. We know that each of these are going to be a function of time. Do we know dx dt? Do we know dy dt? Do we know dz dt? And what are we trying to find? How fast is the distance from the television camera to the rocket? That would be this distance z. How fast is that changing? So this is our question mark. We are told that its speed is 600 feet per second. That's our dy ds. What is our dx dt? What is our dx dt? It's 0, because it's staying at 4,000. So that's a little bit of a tricky thing in this one, that we do know dx dt because it's not changing. So once we've got that, now we can do implicit differentiation of this. And we'll get 2x dx dt plus 2y dy dt equals 2z dz dt. And at the point where the height is 3,000, can you recognize the triangle? How long would the hypotenuse be? 5,000. So first of all, you could plug in 4,000 here, but I'm going to just do it quicker since I know dx dt is 0. I'm going to just call that 0 right away. 2 times y will be 6,000 times the 600 equals 2 times 5,000, which will be 10,000 dz dt. So to get dz dt by itself, we have 36. 5 zeros divided by zeros, we're going to have 1 0. And we are dealing with meters, feet per second. So dz dt is traveling slower than the rocket. Theoretically, does it make sense that the hypotenuse, the speed of the hypotenuse would be slower than its upward speed? How much it's changing. At first it might feel like that's wrong, right? Because your hypotenuse should always be longer. Okay? But if we're talking about a speed, now think especially right at the bottom. We're talking about how fast the hypotenuse is changing, not its length. So if we really imagined it right at the beginning, right, this to that might be a faster increase than that tiny increase there. Eventually, as the rocket gets really, really high and the hypotenuse and it's almost parallel, then they would be traveling almost at the same speed. Yeah.
Since we know that the x would be constant,
Mm-hmm.
could we at the beginning, when we're having x squared, is there already write 4,000 squared?
Now, as that rocket is going up, what is happening is there's an angle theta here. I'm just going to erase some of those blue lines. There's an angle theta here that's increasing as well. how fast is that angle changing? So again, we know that y is changing. We know that the hypotenuse is changing. We need to come up with some sort of equation that relates what we know, dy dt, with the angle. What kind of equation could we create that relates that angle, theta, tangent, right? Because tan of theta would be opposite, which is y, over the adjacent, which stays constant at 4,000. This time I'll put 4,000 in. We could have put x in and then dx dt, but then we get a bunch of zeros. But since it's a constant, it's a good idea to write it in as 4,000. And now we can differentiate with respect to time. Because again, we want to find d theta dt, and we know dy dt is 600. So if we can get an equation that relates those two, which we did, we're going to be able to take the derivative with respect to time to both sides and then be able to solve for it. Of course, it does have the variable theta. That's another thing that we're going to have to figure out. If we know theta here, and we have the triangle at 3,000, could you figure out theta? Yeah. And I'm going to show you two ways that we can go once we take the derivative. So if we take the derivative with respect to time of both sides, what is the derivative of tan? Is it minus secant squared or just secant squared? Just secant squared. So secant squared theta, d theta dt, because it's chain rule. And over here, we're going to get 1 over 4,000 dy dt. So to get d theta dt by itself, 1 over 4,000. We know dy dt is 600. And we would have to multiply by 1 over secant squared. Or divide everything by secant squared. Two ways to go from here. Do you want to see the nice looking way first? Or the more intuitive way first? More intuitive way is the way you'd probably think. And the nice way would be a little bit shorter. What would you like to see first? Okay, more intuitive ways, I have to find what theta is. Theta is not hard to find. I look at my original triangle, and from my original triangle, I know that tan theta would be 3,000 over 4,000. So I just have to go to my calculator and go tan inverse. And when I do that, we'll make sure that we'll deal in radians here. So tan inverse of 0.75 is 0.64, 0.6435 is what our angle is in radians. And then, so I'm doing this way first, d theta dt would equal 600 over 4,000 times, now 1 over secant squared is the same thing as cos squared of 0.6435. And I just type that all into my calculator at once. And I get 0.96. That's pretty intuitive. That's why I need theta. I can find theta for my triangle, so I can just plug it in. Okay? A little bit less intuitive, but a little bit nicer looking per se is, again, 1 over secant squared is cos squared. If I go back to my original triangle, right, at 3,000, here's my theta, 3,000 here, 4,000 here, We knew this was 5,000. What is cos of theta without finding theta? Adjacent over hypotenuse, which reduces to just 4/5. So what would cos squared theta be? Four-fifths squared. Now, just to make sure I'm not lying, I'll type that into my calculator as well. Oh, 0.096, yes. And this would be radians per, what was our time? Second? 0.096 radians per second. Yeah, I forgot the 0 on that side too. There we go. They did both on my calculator show up to the same number. I'm not just making that up. 0.0, that looks ugly. Let's make it pretty. 0.096 radians per second. 0.096. Okay, so I'm going to give you this one to try, and then I'm going to give you a handout, and we're going to work on related rate problems for the rest of class. Yes?